Hello, I'm Yuri Belsky. Today you will learn how to use a simple heuristic for framing and reframing problems known as the size-time-cost operator. I need to acknowledge my co-author STCOperatorEdisons21, who helped to update this classical heuristic and to prepare this video. Most likely you have heard of James Dyson, a famous design innovator who created the world's first bagless vacuum cleaner. Many people ask him of the most important skill for a design innovator to possess. James Dyson usually said that the skill of thinking differently is the one. Moreover, that in order to think differently, designers need to formulate their problems and to conceptualize them in novel ways. The skill of framing a problem in a fresh way is fundamental to innovation. If you want to become an innovator, if you want to think differently, as James Dyson did, if you want to propose winning solutions like Dyson, you first need to learn how to frame problems in original ways. The heuristic of size-time-cost operator may help you. It is a simple means for framing tasks, and it can be used to reframe problems far beyond engineering. The heuristic of size-time-cost operator will help you to consider your task constraints related to size, time and cost of your development. These constraints are represented by two limits. They are either non-existing or absolute. As a result of such procedure, you are likely to comprehend your task more accurately and also to see your development from a fresh perspective. On occasions, with the size-time-cost operator heuristic, you may even generate some great ideas for your development. Let us try to learn the heuristic by applying it to a real task. This slide shows a task that was proposed by the Engineers Without Borders as EWB Challenge project in 2016. This project was actually focused on the design of equipment and methods for preserving food for the Republic of Zambia. In order to learn the procedure of the size-time-cost operator heuristic, we will consider this problem as a general project on developing ways of food preservation. As soon as we formulated our task clearly and concisely, and in our case it can be stated as a question how to preserve food, we need to identify the two items that can be considered under 6 unrealistic conditions of size, time and cost of either 0 or infinity. These two items are the object of improvement and the means for improvement. An object is usually represented in the problem statement by a noun or a noun with an adjective. We clearly wish to improve food, so it corresponds to the object. The means of improvement is established by adding the word means to ahead of the word that identifies the action of improvement. The action is usually denoted in a problem statement by a verb. A verb, preserve, identifies the action of improvement here. Therefore, the means of improvement in our case is the means to preserve or the means of preservation. So we have established that the object of improvement in our case is food, and the means of improvement is the means of preservation. We are ready now to consider these two under the 6 unrealistic conditions. Let us start with food. We need to think of what would we do if the size of the food to be preserved was infinitely small. In essence, under this condition we remove all constraints on the food size. It can be very tiny. What we need to do is to reflect on the problem under this constraint. Try to see the problem from a different viewpoint and to record solution ideas that could suit this condition, if such ideas come to mind. The question on what to do if the food size is small raises other questions. Would we actually consider preserving very small amount of food? What size of food must be for us to consider preserving it in the first place? Are there any simple means of keeping a small amount of food fresh that were used by people over the centuries? Clearly, small amount of food can be preserved by means of the existing technology. A fridge is one of the options. We can continue our reflection on this condition for much longer. The goal of this educational video is to introduce the heuristic in less than 15 minutes, so we will try to only explain the procedure and leave extensive reflection to the viewers. The next step is to put ourselves under infinite food size constraint. We need to think of what we would do if the food size were infinitely big. As in the previous step, it is required to see how this new condition changes the problem. More questions arise. Can we choose the way to preserve food on the basis of its size? If the amount of food is significant, we may need to establish some suitable natural conditions for preservation. For example, most of us have eaten sun-dried fruits. This means that preservation of some products can be done by sun. Underground storage rooms, which keep products under low temperature both in winter and in summer, like wine cellars, is another well-known example of natural storage that can be used to preserve huge amounts of food. Here is the next condition with no constraint. What would we do to preserve food for a very short period of time? Continuing our reflection, we may suggest that the action depends on the food to preserve. It might deteriorate very slowly, and it could be safe to eat this food without preservation. So, we may not need to preserve it at all. This slide suggests us to consider the fourth condition that corresponds to infinite constraint on the time for food preservation. You may say that it is impossible to preserve food forever. Nonetheless, you might be aware that many countries have strategic food storage spaces, usually underground, that keep all kinds of food for 10 or more years. Also, after 10 years in storage, this food goes to supermarkets, and the storage is replenished by fresh products. Certainly, 10 years is not infinity, but it is long enough. This is another condition with no constraint. We need to think what we would do if the food were really inexpensive. Do we really need to invest into preserving inexpensive food? Some of us may even suggest that it is wiser to offer food to others for free rather than to think of its preservation. We have finally reached the sixth condition. This time it is of the infinite challenge. Food to be preserved is very expensive. Interesting challenge, isn't it? Please think of it yourself. I am certain that you will be able to reflect on the task under this constraint on your own and frame it accordingly. Let us instead summarize our experience with the size-time-cost-operator heuristic and remind ourselves what to be done next. What we have done so far was, first of all, we established the object and the means of our improvement. Secondly, we considered the object under 6 constraints. And thirdly, we reflected our task under these 6 conditions and proposed some solution ideas. As a result, we started to see that the problem can be viewed differently under different conditions. Situation with small amount of food to preserve is vastly different to that when we have to preserve huge food amounts. The cost of food to preserve may entirely change the whole approach to its preservation. Duration of food preservation can also transform our thinking and what we need to do with the food. Such reflections and conclusions are the most important outcomes of the size-time-cost operator heuristic. They help us to see our problem in novel ways and from many viewpoints. Well, we've done our reflection for the object of improvement, for the food. Now we need to consider the means of improvement and repeat step 2 and step 3 of the procedure, considering the means for preservation of food. As before, we start with the size constraints. First of all, the size of 0 condition is considered. You may remember that this was a condition of no constraint when we looked at the food. The amount of food to preserve was very small then. This time, this condition represents the infinite constraint on the means of preservation. It has to be very small. Our action after formulating this constraint is still the same. We need to reflect on how this constraint changes the problem and, if possible, record solution ideas. Then we move to the size of infinity constraint. For the means of preservation, this represents the absence of any constraint on the size of the means of preservation. It can be of any size. The next set of constraints are of the time dimension. We need to reflect on the problem when preservation means must either preserve food instantly or are allowed as much time to preserve food as needed. Again, our action after formulating these constraints are the same. We reflect on the problem under these new conditions and think of solution ideas. The last set of constraints are related to cost. Again, we reflect on the problem, this time considering preservation means that are either entirely free or infinitely expensive. And as under all other conditions, we reflect on our task under this new set of constraints and try to see the problem anew and to record solution ideas. Basically, we have walked all the way, and the procedure of the size-time-cost operator heuristic has to be clear to you now. Here is the complete procedure of the heuristic. In order to comprehend your problem and to frame it well, you need to follow these 5 steps and try to consider 12 unrealistic conditions altogether. 6 for the object of improvement and 6 for the means for improvement. Please keep it in mind that problems we face are not the same, and on occasion some of these 12 conditions might not have much sense then formulated. Leave them then. So you may reflect only on 9 or 10 constraints instead. Be flexible applying this heuristic, as applying any heuristic. Let us spend a few minutes to comprehend how and why does the heuristic of the size-time-cost operator really work, and how and why it actually can help us to see our problem afresh. I will use the pendulum analogy for the purpose, the pendulum of constraints, which we see in this slide for the task as it is given. Normally, we do not reflect on our problem by changing constraints significantly. If we have to deliver our product, say, in 12 months, we may think how to design it a month ahead of a schedule. This is depicted by the movement of the pendulum to the right and the increase of constraints, C+. It is unlikely that we will think of finishing the works on our product in just 2 months instead. We also think of how to avoid unexpected delays and what we may do if the development will lag and take longer than 12 months. This is depicted by the move of the pendulum to the left and the reduction of the constraints, C-. We would never, though, think of a 12 years delay. Similarly, when a budget of $1 million is given, we may think of saving 10 to 15% of it, but are unlikely to consider developing the product for a cost of, say, $1,000 instead. In other words, a swing of constraints we usually consider is small. We do not travel far from the constraints that have been originally given to us. The size-time-cost operator engages us in putting constraints to the limits. One of no constraint and another one with absolute or infinite constraint. In essence, we can represent our experience with the size-time-cost operator as a pendulum, which moves us from no constraint to complete constraint for each of the three dimensions: size, time, and cost. Also, characteristics of size, time, and cost usually represent actual constraints in majority of projects. Therefore, questioning assumptions and forcing ourselves on the limits of these characteristics helps us to comprehend our task much more clearly and often differently to the way the task is seen traditionally. Here is the Dyson G-Force, the fast vacuum cleaner that used dual cyclone separation technology. James Dyson launched it in 1983 in Japan with a price tag of around £2,000. This vacuum cleaner started the Dyson empire, and the reason it came to existence was simple. Dyson really disliked dust bags and framed his task as developing a bagless vacuum cleaner. Today, you've learned the simple heuristic of size-time-cost operator. Use it, and it may help you to frame your problem in novel ways and to become a great design innovator like James Dyson. Please consider using the self-learning resources from www.edisons21.com to learn more thinking heuristics.